Hello, my name is SungWon Lee. The topic of my presentation is Malware visualization and similarity via tracking binary execution paths. The contents of the study will be presented in the order of instruction, proposed method, experiment, and discussion conclusions. Before going into the main text, let's start with an introduction. Recently, with the rapid development of network and ICT technologies, the amount of malware has been increasing exponentially. Such high growth rate of malware and malware variant cause increases in malware analysis efforts and analysis time, leading to serious social cost. To cope with the foregoing problem, efficiency analysis method for and study of malware are required. Although the main analysis method is based on static analysis because it is conducted at the code level, the effort the effect of dynamic analysis can be expected because it traces the binary execution path that grasps the behavior. In addition, in the present study, malicious behavior are analyzed through the API collected during analysis, and malware is made into images based on the frequencies and interaction of the API. Since the act of malware imaging as such can be visually analyzed, and malware variants and similar pieces of malware can be easily analyzed through comparison between different pieces of malware. The similarity of malware imaging are also calculated. In the main text, I will explain the detailed proposed method. In the present study, paths are embedded into normal, true, and false ones according to branch instructions before performing path searches. In addition, the APIs appearing during searches will be collected to organize mutual relation between the APIs to show the malicious behavior. I will explain it through example code. The corresponding code branch from local 40178884 into local 4185DD when it has been found to be true through the comparison instruction on the 7th line, and local 4185DD branches into local 428986 when it has been found to be true through the comparison instruction. The 50th through the 21st line are the same searches process, and local 4268DE is defined as a normal mark instead of true or false mark because the subroutine sub 488930 is simply called in line 23 without any comparison instruction. The mutual relationship between the instruction set and the subroutine can be visualized as shown on the right. Next, the normal, true, and false mark application mechanism is applied to the APIs called in line 46, 11, 17, and 26 of the code. The interaction between API and behavior of the API is visualized as shown in the right figure. After going through several steps, the code on the left is finally visualized as shown in the figure on the right. The previous example was intended for the piece of code. However, it is difficult to express all of them because there are too many API for actual samples. When all API are used for graph imaging, the analysis time may be too long and the readability may be degraded. In this study, API are reclassified into 25 upper categories to make clear judgment and increase time efficiency. Such a classification not only has many categories to which API commonly belong, although they have been already classified in MSDN, but also is too abstract to understanding behaviors. For instance, all process-related APIs are included in the categories process, but whether the relevant API creates, delete, or access processes cannot be known. In the present study, the mutual relation of API were marked as normal, true, or false using static execution path searches to analyze the action. The frequencies in the entire binary code in relation to the foregoing can be again made into a matrix, which will be used for the finally visualization later. There are 25 API categories which indicate the API actions, and since the actions are again marked as normal, true, or false, the frequencies were shown with 3 25 by 25 matrices. Tables show examples to show the frequencies of the mutual action of API categories made into matrix, which show example of mutual calling relation ranging from 0 time to 5 times. Although only 3 categories, file create or open, handler, and system information are shown in the relevant tables. They are just to show examples, and all the 25 API categories are referred to for the final frequencies of mutual relation of API in the present study. 25 categories API node and edges related to normal, true, and false mark are visualized to identify malicious behavior. The information used for the visualization consists of 25 categories API nodes and frequencies related to normal, true, and false mark. Table shows compositions of graph visualization. Table show composition of graph visualization. 25 nodes are fixed as absolute paths, and mark constitute the color information of H with R, G, and B color respectively. The RGB colors consisting of 0 to 255 increase by 50 every time the frequency of the mark increases. For instance, left table, since the frequency numbers of system information are normal 4, true 1, and false 2, the color information RGB of the H consists of 200, 50, and 100. Finally, the frequencies number of API mutual action in table are integrated as shown in right table and are visualized into graph as shown in figure. In the present study, finally, the entire action of malware are made into images, and similarity are calculated based on the relevant images. Figure shows the graph made by the imaging of the malicious behavior, which is actual malware, according to the proposed method. Each fixed node consists of API categories, and the colors of edges connected between the nodes have RGB values that change the frequency number of mutual action of the API. The graphic images as such enable malicious behavior analysis through the identification of API interactions. However, the graphic images as such are not suitable for calculation of similarity because the malicious behavior in the present study are shown as API categories expressed with node and interaction expressed with edge and adaptability, and occurrence cannot be expected from similarity calculated with the color information and the information such as the shape of edges. This is because when color information on graphic images is enlarged into pixel units, other colors than the colors of the edge appear due to this distortion. Therefore, in the present study, API's mutual actions are reconverted into simple 25 by 25 pixels images and used in the calculation of the similarities. Figure shows the method of changing API mutual action into 25 by 25 pixel images according to new API sum metrics made by summing up the three API metrics for normal, true, and false action in the method of proposed. In the present study, the similarity of malware variant and similar malware will be calculated based on the pixel image as such. 25 API nodes composed of absolute phase frequency number related to normal, true, and false actions are constructed into R, G, and B color information, respectively for visualization. The similarity of the malware images in which the action were expressed as such can be compared through color comparison between pixels. The similarity of the colors of all pieces of pixel information on two images being compared are calculated through the algorithm for Euclidean distance in the color space. Figure shows 6 by 6 pixel images intended to present example of pixel images similarity calculation, and the pixels were enlarged for easy understanding. 1 square means 1 pixel. The similarity between the color distance per pixel of these two images become closer to 1 as the color becoming more similar, and it can be seen that RGB are 99% similarity color. Therefore, if the colors of all the pixels of the two images are the same, color similarity is calculated as 1. Now that the theoretical part of the proposed method has been explained, I will explain the analysis by results of the example. Malware is made into 25 by 25 pixel images, and the similarities are calculated. The similarities of different pieces of malware will be verified based on the similarity of the image of the relevant piece of malware. Three pieces of malware in three families, which are juicy, conflicker, and deburm, will be randomly selected, and the similarity will be verified. Figure shows the malicious behavior of malware juicy made into pixel images. It can be seen the juicy use complex API because the pixels are evenly distributed. However, compared to juicy, conflicker, and deburm show intensively distributed pixels on same parts. This malicious behavior pixel image can be used as a basic data to grasp in malicious behavior through the API. Based on the malicious behavior pixel image as such, the API being manually used can be identified and the result can be used as basic data to understanding malicious behavior. In the present study, the similarity of the malicious behavior pixel image shown in figure will measure using the color distance method proposed in this paper. The results are as shown in tables. First, with regard to juicy, although the pixels are evenly distributed, it can be seen that the position and color of the pixel in 3 pieces of malware are shown to be similar. Therefore, the similarity were calculated to be at least 75%. In the case of conflict and deburn, the the fact the fact that the positions the pixels indicated by the color are intensive and the colors are similar can be seen through the calculated similarity 82%. The similarities of other pieces of malware than the 3 malware families experimented as explained will be measured. Left table lists the malware families experimented in the present study. A total of 12 malware families and 930 malware samples were experimented. In the present study, all the malware samples include IAT because binary analysis-based API are collected to analyze malicious behavior. The right table shows the minimum, maximum, and average similarity of the malware families. For all the families, average similarity that lower than 73% are shown. However, the growth rate of malware is currently increasing exponentially, and analysis for this discrimination of new malware variant is necessary. To that end, in the present study, 10 randomly selected pieces of malware were made into pixel images and compared with pixel images of malicious behavior experienced earlier to experiment the detection of malware variants. In the table, the right end shows the detection result. In this experiment, 8 out of 10 pieces of malware were classified to coincide with their families. However, 2 pieces of malware were classified differently from the detection result. This is due to the fact that analysis same for the relevant malware families were not prepared. In addition, the reason why the result of classification of these 2 families were shown to be cozy and KZ is that among the family samples experimented earlier in the presented study, the number of samples in Juicy and KZ family were overwhelmingly larger. However, this is a limitation that can be resolved by preparing analysis samples for malware families. Although so many families analysis samples were prepared in the present study due to difficulty in the collection of malware sample, the accuracy will be enhanced through continuous sample collection and analysis sample data construction. 3 previous methods for measuring malware similarity and the method composed in the present study will be comparing the term of analysis and time. All the 4 methods, including the proposed method, indicate higher similarity when the values are closer to 100 and indicate the average value of similarity. The similarity of families with at least 100 samples such as Kuzi, KZ, and Kaftar were calculated to be 70%, and the methods composed in the presented study show higher similarities than other methods. This can highlight efficiency and automating the analysis of the large number of malware by calculating similarity to other similarity methods, even for a family of large number of samples. This means that the method proposed in the present study will calculate similarities to be higher than other similarity verification methods even in the case of families consisting of many samples, highlighting its efficiency in automating for analysis of massive malware. Finally, the conclusion. In the present study, malware was analyzed at the code level using static execution path searches. API were nodalized and the mutual action of API were visualized as edge and the color of the edge. The education distance algorithm was applied to measure color similarity, and the similarity of visual malicious behavior are calculated based on the final value of education distance. Finally, the similarities calculation based on the similarities based finally the similarity calculated based on such methods were compared with the similarity calculated using existing similarity calculation method, and it was found that the similarity were calculated to be 5% to 10% higher on average by such method.